Okay, so we'll start the recording and just see when people start coming in. We'll give it about 5 minutes. Okay, hello everyone. If you're here, just say hello in the chat once you're logged in. Okay, we'll get started in the next couple minutes. Just want to see if people are coming in. See if you're here, go ahead and send us a chat. Go ahead and type hello in the chat. Hey, Joseph. Okay, when one more minute, we'll get started, and as people start rolling in, they can go ahead and follow along with us. So one more minute, and then we'll get started. All right, so I'll get us started. Thank you everyone for joining us on behalf of MESA for our virtual career visit series. This is our second career visit that we've done this year. And before we get started, I just wanted to do some quick announcements. So I know that we're all joining virtually, but MESA is located at Portland State University, and Portland State University is located in the heart of downtown Portland in Multnomah County. We honor the indigenous people whose traditional and ancestral homelands we stand on, the Multnomah, the Cathlamet, the Clackamas, Tumwater, Watalala bands of Chinook, the Tualatin, Kalapuya, and many other indigenous nations of the Columbia River. It's important to acknowledge the ancestors of this place and to recognize that we are here because of the sacrifices forced upon them. In remembering these communities, we honor their legacy, their lives, and their descendants. And I apologize if I butchered any of those names. Community agreements. So we just want to remind everyone, even though there's a public chat available, to be respectful, listen to understand, listen actively and attentively. Don't be afraid to ask questions, and I'll talk about questions in a minute. Allow yourselves to be uncomfortable and assume positive intentions. Just so everyone knows, for any questions as our presenters go along, you can type questions in the Q&A. All you have to do is click on that light gray Q&A. It will turn into a darker gray or black color, and then you can type your questions as we go along. Other people will be able to see the questions, and if you have the same question, you can upvote it. So the question that gets the most upvotes will be answered first. I'd like to introduce our presenters from Simplexity Product Development. We're joined by CEO Dorota Shortell, along with Kim Morsch, DJ Weeks, Kristen Pollock, Charles Fleck, and Michelle Gustad. And with that, I will turn the floor over to them.
All right, thanks, Bianca. Can you share our slides then now?
Yes.
Okay, that would be great. So that is, could we just go to the first slide? That's the last slide. Thank you. There we go. So yeah, I'm Dorota Shortell. I'm the CEO of Simplexity. I'm located here in Portland, Oregon. I live in Portland, Oregon, and our local office is across the river in Vancouver, Washington. And I'm also a mechanical engineer by training. And I'll let the other members of our team introduce themselves in the order that's on this slide. And you have to unmute.
Hi, I'm Kim Morsch, project manager at Simplexity. And I'm out of our San Diego office.
I'm DJ Weeks. I'm a mechanical engineer at Simplexity out of the Vancouver office.
I'm Kristen Pollock, electrical engineer out of the Vancouver office.
And I'm Charles, and I'm a firmware engineer out of the Seattle office.
All right, thanks. So with that, our plan today is to give you an update on what engineers do. And so we have each of the different engineering disciplines that are going to go through that, and then we'll have a virtual tour of the office. So we're going to start here with DJ. Why don't you go ahead?
Sure. So engineering is all about solving problems, and it's definitely a necessity that all our different disciplines work together to solve those problems effectively. But we're going to kind of go through each of them with our own disciplines that we know the most about. So I'm a mechanical engineer. That's anything that you can touch, anything that moves. So gears, pulleys, structures, it's all mechanical engineering. And how I got into mechanical engineering, I was definitely math and science oriented throughout school. What really pushed me there, though, was I had a really great physics teacher in high school where everything was hands-on, and everything we learned, you were able to prove it to yourself. And I've always been fascinated with how things work. And so that kind of logically led me to mechanical engineering. I went to school in the Bay Area at University of California, Berkeley, and stayed on for a master's there, and then came up to Simplexity after that. So on any given process, we go through this cycle of product development, or any given product rather. And the first step is ideation. So that involves a lot of whiteboard sketching, brainstorming, and sitting around a table throwing out ideas for how is this thing going to come together. You start with a list of requirements, and you need to figure out how to translate those requirements into a physical product that will do the things you're asked to do. So if you've taken any physics classes, you might recognize this drawing on the right as a force diagram. Doing simple force diagrams like that are a way that we can save a lot of development work, rather than this is an easel and the question was, how wide does the base have to be so that when you draw on it, it's not going to tip over. That's something that could be really expensive and time consuming if you want to make easels with a bunch of different base sizes, or if you do a simple force diagram, you can save all that work and get it out in a couple minutes. Once you have your basic idea and your architecture figured out, we go into what we call CAD, which stands for Computer Aided Design. And that way we can make 3D models of our parts so we can really get a better idea of how do they fit together, how do they look, how do they work, things like are they going to be held together with glue or snaps or screws? And if we're using screws, where do they go? How many do we have room for? Making sure that the parts can actually be made. That's all done in CAD. And CAD also enables us to perform some analysis. So if you imagine that this plate is your phone and you want to see if let's draw here, if I'm holding on this corner and pushing on this corner with a certain amount of force, and we're going to break the phone, one way we can do that is by running a finite element analysis on our part. So this is what it might look like under that situation. I guess I picked the wrong corners, but you can see the distribution of stresses throughout the part. You can see where it's at risk of breaking. And that way, once again, without having to go through all the time and money of making parts, you can see where you might need to beef them up, or maybe you need to choose a different material or a different geometry for those parts. And then finally, the part that is, in my opinion, not only most important, but most rewarding is prototyping your parts. Once you're looking at them on a computer screen for weeks, sometimes months, and then you have the parts in front of you, it brings it all to life. And that way you can really learn things that, as important as it is to do whiteboard sketches and back of the envelope calculations and even finite element analysis calculations, it really doesn't compare to what you learn when you actually hold the thing in your hand and you can move it around and feel it. And so we want to test early and test often. And then from there, you're going to learn things that will take you right back to the whiteboard. You'll draw out new sketches, come up with tweaks to the design, and go through the whole process again until you have something that really works the way you want it to and meets all those requirements.
All right, so on to electrical engineering. So this is more about, how do we actually make these things turn on blinky lights and screens and move motors, all of the fun parts of making electrons move around. So in terms of how did I get into this, in school, I was really interested in the environment and in physics. So I ended up going to college for physics in undergrad, and then got a job working in a solar panel manufacturing plant doing research and development. And while there, I got to see all of these different branches of engineering and realized that electrical engineering seemed like a lot of fun. So I went back to school for that, and ended up at Simplexity, where, I get to do a lot of electrical engineering, but it's nice working here. You get to kind of dabble in lots of different areas if you want to. So. So the thing that I work on day to day is designing these things, which are called printed circuit boards. So inside all of your cell phones, microwaves, or even your toaster nowadays, there will be these printed circuit boards, and you need to figure out where all of those components go and how they're connected together. So on these green boards, you'll see all these little black boxes and little rectangles, which are computer chips and resistors and capacitors and all of the components of electrical engineering. So the first step to that is to design the schematic. So this is just a symbolic representation of how all of these little components are connected together. So you see on the screen here is a field effect transistor and resistor, and all of the lines connecting them together is showing how each of those blocks are going to connect. Additionally, you may at this stage do something where you're modeling with the software to figure out, okay, if I use this voltage, what's the current going to be, and making sure that your design is going to work before you even have anything physical to work with. So after the schematic, you move into layout. So you saw on the first, that green image, inside that board, there's all of these different layers of copper and vias that move from layer to layer. So on the computer, you have to determine how all of these chips are going to be connected together so that they can work nicely. And it's kind of like an art project sometimes, because you're drawing all of these lines and it ends up looking really beautiful on the screen here with different layers being represented by different colors. So it's one of my favorite parts of the electrical engineering process. So then once these are done, you bundle up the files and you send them off to a fabricator to get actually made, so that you get back something like on the left here is a printed circuit board with the chips soldered on. And at that point, you get to do the hard part of making sure that it actually works. So you plug in your battery and you can measure the voltage and current with something like on the top right is called a multimeter. Or you might use something like on the bottom right there is an oscilloscope where you're measuring the voltage over time. So you can make sure that any computer chips that are on there are wiggling all of their signals at the right frequency and the right voltage levels that you expect them to be. And probably the final step will be, once you have all of that done, you're sure the board is working well, you put it all together into the mechanical design, and you can press the buttons and make sure the LEDs are turning on when you expect them to. You can try to connect to it over Bluetooth on your phone, or all of the kind of functional testing that is the end goal. All right.
Hey, so I'm here to talk about software and firmware. So the difference between software and firmware is software is kind of a higher level coding opposed to firmware. So software is usually apps that are run on like a computer or a phone. So something like Spotify, that you open it on your phone and then it has a UI that you interact with, and you don't really care what's going on with the hardware. That's all done with lower level drivers. Whereas firmware is something that is directly interacting with the hardware. So like if you have a toaster, it's gonna, like Kirsten said, if you have a knob that turns on how long it's gonna last, you have a button to turn it on. So that's all inputs that the toaster is gonna take in, and then it's gonna wait for that time to go on, or turn the heat on, and then once the time runs out, it'll pop it up and be done with it. So it's more directly interacting with the hardware itself. So how I got here, in middle school, I wanted to be a musician. So I went to an art school and I realized that was probably not going to happen. So I switched over to a math school to learn math, like a STEM focused program. And when I went to college, I wanted to pursue math, but I also figured engineering would be a more interesting career for me. So I chose electrical engineering, did some internships. And although I was building really cool stuff, and I thought it was really cool how like you can plug a TV in and an antenna and like see signals through the sky and just make an image out of that. I wasn't getting to play with all the fun stuff, and I was noticing the firmware engineers got to like program the motors and move everything and turn on the LEDs. So I switched over to that, and then once you do firmware, you kind of end up doing some software as well. So it kind of doesn't really matter how you get there. There's a lot of different paths you can take. You don't have to be a computer engineer or computer scientist to get into firmware. And I think the EE background even helps a little bit to understand how the hardware works. So what I usually do, the first thing is a lot of communication. I feel like there's kind of this stereotype Dilbert kind of guy that is the engineer. And I think that's a pretty bad stereotype. There's a lot of diverse people. And there's a huge amount of like communicating with other people, talking to the clients about what the requirements are, so you can know exactly what they want and you can make them happy. You have to talk to mechanical engineers to figure out, oh, what are the gears that I'm going to be moving? Do I have to drive this motor? How does that work? Talking to electrical engineers to help debug, to help figure out, oh, is the processor hooked up to these things in ways that are actually going to function? So that's a huge amount of it, is mostly just talking to people. But so the actual process is we usually start out architecting the system with things like this chart on the left, which is just a state diagram showing the system flow of any thread in a process. So you kind of architect it out like that, so you know how the code's going to work, how it's going to interact with other sections. And then we get things like this dev kit on the right side. And that's just basically a processor with a bunch of pins pulled out of it and a programmer. So it's really easy to test your code on it. You can hook it up to like an accelerometer, test that out. It's really useful for just helping design the system and proving it'll work. And so from there, so here's like a little bit of code. So you do the coding on there, and then eventually you're going to upgrade to the actual hardware, which you'll go through a few revs of that to make sure that everything works fine, and everything's up to standards. It meets all the requirements. But so a big part of it is also debugging, which is probably what I spend most of my time doing. And there's a lot of different methods for that. There's debuggers that let you step through the code and make sure that all the registers in the processor are set properly and everything is following the flow you expect it to, because usually the problems are you told it to do something that you didn't mean to. The processor never messes up. There's also, you can blink LEDs. You can make a command line interface to just print stuff out to a computer so you can read things. And then there's things like Kristen was talking about earlier, like you can take an oscilloscope and look at the signals. This thing at the bottom is actually a signal analyzer, just looking at a processor talking to another chip. I think it's an accelerometer, just to make sure that the accelerometer is responding and everything looks nice. But that's about it. A lot of talking to people, a lot of debugging, and then a little bit of coding.
Okay, thank you. So project management. What project management is the project managers typically lead the projects, and they're bringing together the client teams and the engineering teams to work together toward a common goal of delivering a robust product that meets the client's expectations. The project manager will facilitate defining the requirements, which you heard both Charles and DJ mention, and the success criteria. They help organize the team brainstorming and design development, and they generally keep the project moving forward, ideally on schedule and within the client's budget. Often this can feel a little bit like herding cats. So that is our primary job. So what skills are needed for project management? A project manager should have excellent communication skills. They have to drive meetings with both clients and the design teams. They have to keep the project documented and organized, and they need to make sure all stakeholders in a project get the information that they need. And the key is to keep both teams on track and on the same page. The project manager should be able to multitask and be organized, as well as understand and manage the project finances. We have various pieces of software we use to manage both finances and schedules. So most importantly, every project has risk. Problems crop up because that's the way the world works. So the project manager helps lead the team to decide how to resolve these issues and move forward. So how did I get here? I have both my bachelor's and master's degree in mechanical engineering, and I started my career as a mechanical engineer in product design. This was my original job at Simplexity as well. As we grew in size, though, we needed that in order to handle more projects and more people, we needed to dedicate some people to project management. as someone who enjoys working with a lot of different projects and people, this was a good fit for me. Another group of people that we have at Simplexity is our technician group. Our technicians are critical for our builds of both prototypes and finished tools. They have many roles at Simplexity: modifying parts, managing the purchasing, assembly, build, and test of our prototypes and our tools. Most of our building happens at our two largest sites, which is our Vancouver, Washington site and our San Diego site. So those are the sites that have our technicians. This slide is showing one of our technicians in Vancouver in the machine shop on the lathe. You'll also find our technicians soldering, building electrical cables. That's something they often do. You'll find mechanical assembly. In this case, due to COVID, we've taken over all of our conference rooms and we're assembling in every space, in every spot at both buildings. And then you'll find us building production tools, fairly large tools that involve pretty complex inputs, and anywhere from pneumatic assemblies to electrical to mechanical assemblies. Okay.
All right, so that brings us to the virtual tour. So if we could get that video loaded, and then instead of the slides, then we've got a tour of me walking through our office. Since we couldn't physically have you come to our office this time, we did shoot a video there, so you can watch me there and see how the office looks.
Hello, welcome to Simplexity. This is our Vancouver, Washington office in the Portland, Oregon metro region. We're just about 15 minutes north of the airport. So this is our front entryway. And here we have Marion. She is our office manager and accountant and does all sorts of tasks to make the office run well. Over here we have what's typically our conference room. And you can see our conference rooms are actually named after squirrels. So this conference room is named Cypress. We'll see the other conference rooms. And as you can see here, we have now, during COVID times, turned a conference room into a build room. So here at Simplexity, we design and build all sorts of hardware. Stephen over here is assembling some parts. He's a mechanical engineer. And so not only do our engineers help design and figure out what to do, but once the parts are in, they help put them together and make sure they actually work. So we don't do high volume manufacturing, but we do always build a few to make sure that they work and they come together. And so we have our engineers help do that. We also have technicians that sometimes do it once it's proven out. But when the product is just being designed, there's always things that don't work. That's part of the design process. And I know a number of you are familiar with the design process, and then putting things together, seeing what works, seeing what doesn't work is always part of that process. Some of the other items we have in here are things that we've designed. So this is a mechatronics board, and this basically acts as a development board. So when we were designing, for example, the 3D printer, the firmware engineers need to write the code, but if they don't have a board to write the code, they have to wait for the electrical engineers to design the board. So this board kind of serves as that board to do the development on, and then we convert it to an actual production board that would go into the product. This here is a battery. It just looks like a AA battery, but this is actually for OSIA, and they have wireless charging. So basically this is called the Forever battery. And we designed the board, and you can see this really tiny board that goes inside of that. And so if you've got a product that normally needs AA batteries, they have a module where it'll charge it wirelessly. So there's a module in the room, and it charges the batteries without touching them. And so this battery will stay in the product, and it'll keep charging forever and ever. Some of the other parts that we've designed, this is an older wearable product from the Microsoft Band. It's now been discontinued. But this Microsoft Band has a metal part in there, that's the structure. And we designed, our mechanical engineers designed the sheet metal stamping to have that stiffness. And we also did a lot of finite element analysis to make sure that as this flexed many, many thousands of times, that it wouldn't break. This is the disassembled valve VR system. And so we had a lot of electrical engineers who designed all of these flexible cables and these boards that go inside, and then we did some of the firmware inside of the unit. This actually sits, this is part, you can see the goggles. And so our team designed all of these parts that go inside this VR headset. And then we've also done this product, which is a strobing glasses. So what this is used for is, and this doesn't have the strap on the back, but you put it on and the glasses strobe on and off. And so if you're trying to train for, let's say, basketball, you actually wear these during training. And so it makes you, makes your brain interpolate and makes your brain kind of have to react faster because your vision is blocked, and there's a correlation between your vision and your brain. So as the ball is thrown to you, your vision's blocked for just a fraction of a second. And so then you can react faster. And so then during the gameplay, you don't wear the glasses. This is just for training. Then your brain has been trained just like your muscles are trained to react faster. And there's also medical applications for this product. So that's the housing. We designed that, as well as you can see, here's the lenses with a flexible cable that's attached to that. And then over here, this is how these parts are made. They're made all together in one panel. And you can see there's 5 of them, and then they get punched out of this panel. And very early, these are rapid prototype parts as well for the glasses of how they looked. So this is early prototype parts of that, and that's the case for this product. So over here, we have what looks like a printer. It's called the HP Envy. And what we did actually is we redesigned this printer with HP to go on the International Space Station. So it couldn't have glass, so the glass got replaced. And then we had to figure out the trays so that the paper wouldn't float away in a zero gravity environment. So we redesigned the trays, figured out how the paper would go, and there's actually 2 of these on the International Space Station right now that Simplexity designed and built. There were a total of, I think, 24 that were built, and we did build all of those at Simplexity. All right, let's keep walking down the hall. All right, so now we're walking through the main hall of the office. We're going to walk back towards the machine shop. So as we go through here, you can see that we are here in our machine shop, and here we have Chris. He's our production supervisor.
Hi, how you doing?
And Chris will maybe give us a little bit of a tour here of what happens in the machine shop, and
Sure.
then maybe he can kind of show some of the things that he
Yeah.
does. He's also an expert machinist.
Yeah, there you go, thanks. So yeah, I'm actually getting ready to mill some features on a product on our mill machine over there, and I'm just calculating some of my moves right now. So, you know, there's CNC machines that are prevalent in the world today, but we have a manual machine. So I actually have to kind of calculate what I'm going to do before I do it. But other than that, it's great to have the machine available for us to be able to do quick turnarounds of, prototype and experimental parts. And if you want to come over, I'll show you exactly what I'm talking about. So right now I'm making a clear polycarb panel for the front of a test machine that we're working on. So I've cut out a center hole in it. I have it clamped down. I'm getting ready to machine a groove all around here where there's going to be some other components that fit into it. So again, I have to calculate those moves with the size of my end mill and so on and so forth so that I make it in the correct feature. So, so this is our milling station. We have some common tools, your drill press, your sanders, workstation here in the center with some presses that we can put in bearings and dowel pins, things like that. We also use it with a deburring tool. So a lot of times we're doing prototypes. So oftentimes we have to kind of come in and just sort of, make clearances and hog out things to make them work the way we need. We've got a hydraulic press, and we have around the outskirts of the building, we have supplies. So we've got screws, washers, taps, reamers, things like that. We have some bar stock, and we've got a cutoff saw that we can cut small lengths of things that we then, like bar stock, that we would then be able to put into the lathe and cut some shapes and make, custom parts, standoffs, whatever we might need for our tests. So this is another area. This is our electrical engineering laboratory. Pretty much the EEs they have their set of tools, analyzers, power supplies, things like that, high power scope. They're able to grab boards and do lots of custom soldering and even little tiny surface mount type of things. So we have a really talented group that is able to do a lot of good work on our boards that we're producing, and then we have a little bit of an inspection area here for doing simple things with gauge pins and micrometers and calipers and that kind of thing. We've got like force gauges down there that we use quite a bit in the business to determine, how things are. This is set up right now. We're doing a little run out, accuracy run out on a part that, we just put on there and spin around and measure it with the indicator to make sure it was running out true.
So now that you've seen the EE lab, this is a secured conference room, so we actually do need key card access in order to come in here. Sometimes we have top secret projects. Right now we don't, so I can show you what we have. And the top secret stuff we do have, we actually cover up. So you can see there's some black tarps and cloths of things we can't show. But this allows us, for some of our clients that can't show the projects we're working on, because we're doing a lot of development before products are released to the market. So it's early on, and so a lot of times the projects are confidential and we can't show them. But this room is, again, a build room where we put things together. And this product we can actually show. So this is the SteriFree Aura unit, and we're working on this with SteriFree is the client, and Aura is the name of their product. And what this is a disinfection device. So this is going to go into doctors' offices and hospitals. So instead of the staff having to use wipes to sanitize the stethoscopes and even electronics and cell phones and everything, they would put all of those items into this device, and they would press a button, and then it does a disinfection cycle. And this product uses hydrogen peroxide to disinfect it. So it doesn't have to, like a UV disinfection, it has to be point of sight. And this actually encompasses whatever needs to be disinfected. And so we are doing a redesign on this product to reduce the cost, the weight, make it less loud, so kind of make it a quieter system. And so we're doing all of the system analysis on all the components that are going in there, doing the mechanical design, on all the ducting design, the electrical engineering, and the firmware as to how to control this unit. So that's something that we're working on here, and so that's why we have it different states of disassembly, since we are doing some analysis as to what needs to change in order to make this project even better. And then over here is one of our engineers, DJ, and he's doing some work as well on this project. So he's just pulling up some code on his machine, so you can see that.
Testing the blowers to make sure they're functioning correctly and getting the flow rate that we need.
All right, awesome. Thanks, DJ. This is going back out to our main engineering area. And so as you can see here, this is a wide open area. We have it wide and open for collaboration purposes. Right now, we only have a few engineers here in the office. So we have Vito. Vito, you can turn around and wave and say hello. So we are required to wear masks again during COVID, and normally we'd have engineers at every space in the office, but because of the pandemic, we are encouraging everyone who can work from home to work from home, and they come into the office if they need to build hardware or put things together, but in general, the design work can be done very well from home. So let's just walk around this room a little bit, and you can see some of the other areas. We've got another entryway here, and then you can see there's parts on people's desks. And that's because when you do design, you're also putting things together. We're a very hardware-oriented company, so the electrical engineers have boards, the mechanical engineers have different mechanical parts. The firmware engineers sometimes are debugging hardware, and so then they're also having to have the hardware, and they're writing different code to see what the reaction is of those units as they're writing the code. And then over here, we have a couple engineers, and again, most of them are at home, but we've got Michael over here doing some work. And then, again, a few more empty desks. And then we've got Tristan, he's a mechanical engineer. And then Amy is over here as well. And Amy's another mechanical engineer, and she's looking at some parts that she designed, how those are going to work. And then, she's got the CAD on her machine that she can look and compare and see how those parts came together well. All right, and then that's kind of the main engineering space. And we also then over here have our VR room. And so in the VR room, we have the Valve headset. We actually designed this headset, so we did a lot of the electrical and firmware engineering behind this headset. And so we use this room to then test how that's working. And then it's also a little bit of company culture and fun that we have this VR room set up, so if the engineers are done with their work and they need to relax a little bit and unwind, they can actually come in here and play a little bit of VR games. Well, that concludes the tour of this office. Thank you for joining us today. We're walking back out the main hallway. And again, if you have any questions, you can visit us at simplexitypd.com on our website. We are a product design engineering firm, and we're very pleased that you could join us here. Thank you.
All right. So that gave you a taste of the office without even having to leave your house. So there you go. If we could put the slides back up, perfect. What we wanted to talk to you a little bit about as well here, sorry, advanced too far, is what you can do if you are interested in engineering. So Kim, I think you're going to talk to this slide, and then I'll talk to the next one.
Yeah. So there's a lot of things you can do, even without your engineering degree. There's a lot of ways to experiment and have fun with the similar tools to what that we have. There's free CAD computer-aided design programs online, similar to ones that DJ had mentioned. You can try Onshape, Fusion 360, or Autodesk Inventor. There's plenty of YouTube videos that will teach you how to use each one of those programs. You can learn free programming online. Games and animations can be learned through Scratch and Khan Academy, and those are also free. You can make your own circuit boards. There's circuit board programs similar to the ones that Kristen had shown from Eagle and KiCad. And then you can put it all together. You can experiment with electronics kits. Arduino or Raspberry Pi are fairly inexpensive and allow you to add many different kinds of sensors, motors, all kinds of things, so that you can do your own home projects. And you'll find many resources on the internet for different projects other people have done. They're always willing to share. And the last thing is you can join STEM organizations if you don't have them at your school. There's plenty of organizations out in the community as well. So we have resources download at the end of the presentation with some links.
All right. So we'll share that maybe during the Q&A session or towards the end, where we have links to these resources. And then some of you may be wondering, well, what's the path? And I know each of the speakers so far has talked about their path. I also pursued kind of option one here, the engineer path. This is the most straightforward. So for any of these professions and careers, you do need to get your high school diploma first. So stay in school, do well in school. And then the first option is to go ahead and go straight into an engineering degree from getting a bachelor's degree from an engineering school, which is what I did. I got my mechanical engineering degree. You can also start with community college and then transfer to an engineering program. So like Portland State University or Oregon State University, you can do your first year or two at one of the community colleges and then move to an accredited school. So that is one option. And then you can do a master's degree, that's optional. You can do a PhD, that's not typical. So of our engineers at Simplexity, I'd say maybe half have masters and probably 2 or 3 have PhDs. And then a bachelor's degree is fine. And then again, you get a lot of experience on the job. So that's kind of the traditional route, but you can also take a less traditional route, which is getting a degree in another field, a related field, typically like physics, math, biology. And then you can get a master's degree from an accredited school and then be an engineer. And then in terms of being a project manager, it's a little bit more open. So we typically have engineers who are also project managers, but not only. We have some project managers who have degrees in other areas. Like, for example, one of our project managers has a degree in biology and then has learned how to do project management on the job. You can get a master's degree, you don't have to. And PMP, that's a project manager certification, you can do that. Those are sort of extra classes. It's not a degree program if you want to get into project management. And then technician is the least amount of schooling. So you can get associate's degree, which is usually a 2-year degree, or go to a vocational school to learn. I know that Clark College in Vancouver has a 1, I think, or 1.5-year program that you can become a technician and start working. And then we do have some technicians who then want to go and get more education and become engineers as well. So you can do both. So don't feel like you have to make a decision today or even on the day you graduate from high school. You do the things that interest you, and then you can get the career path to the job that you want and that you like. And there's no reason you can't also go back and get more than 1 degree if you change your mind. So a lot of people do that, and that also works. Okay, and then with that, and you can, again, if you have any questions, you can put them in a chat and we'll answer them afterwards. I did want to share a little bit more case study material. So we touched upon these a little bit in the tour, but so this is the Valve VR headset that I mentioned. We did the electrical design and some of the firmware design on this product. And so this came out, I think, about 2 years ago now from Valve. And just wanted to show you some cool photos of that one. And you can see the insides of it. And I shared some of these during the video tour as well as to what all the parts are. And this was a pretty complex electrical design. And I don't know, Kristen, you didn't work on this, but you probably could talk to this a little better than me in some ways, where there's like rigid boards connected by flexible cables. And so all of that had to be designed, and there was a lot of work and analysis that went into how this is communicating with other parts of the system and making sure there's not interference and noise and so forth, electrical noise. So this was probably a 1.5-year long project with a team of 10 people from our side to design and figure out and make various versions of prototypes to see how this product would work. So you can see some of the boards there. And then these are the board and hooked up to some of the displays that are in the headset itself. And then this is Tim. He's one of our engineers, and he's demoing this unit. And I don't know, can we pull the video? There's a short video of him using the VR headset. And so you can see here, Tim is, this first part is in slow motion, so you can kind of see as he moves his arm, you can see behind him in the screen, he's shooting an arrow at a target. So you can, on the screen, see what he's seeing, except he's seeing it all the way around him. And so playing this game where he's shooting arrows with that VR headset. All right. And then back to the slides. Okay, I think I can hit remove video. All right. So hopefully the slides will come back. All right, perfect. Thank you. So that's one of the projects that we've done, a recent project. This is a slightly older project, but we actually are still building these. So this is a project for TaylorMade Golf, and they're a golf club manufacturer. And this is a project that came to us, I'd like to say, maybe even 10 or 15 years ago now, even more. I was actually still doing mechanical engineering work when this project came to us. So I remember being on the very early phone calls. So the idea behind this is that when people golf, they're really, I guess, picky about their game. I'm not a golfer, but I hear that that's the case. And so having the perfect clubs will affect the game. And so rather than just buying clubs off the shelf, before they had this machine, people would bring their clubs back to tune them, and they'd adjust the angle between the long handle and shaft of the club and the face of the club when it had these lie angle kind of lines that show. And so what they did in the past is that there was someone who would clamp it, and then they just like apply a big crowbar and they kind of just yank on it to try to fix the angle without any feedback. And they just kind of do that by eye against like a paper printout of an angle. And so what they asked us to do is to develop an automated and more accurate way of adjusting golf clubs to the, I guess, ideal angle for that individual. And so here on this slide, you can see on the left is the CAD of the machine that we designed, and I designed a lot of these sheet metal enclosure. And then on the right is a picture of it that we built, and we've built, I think, 10 of these now in our San Diego office over the last 10 years. So it's not a whole bunch, but it's one or two a year. We'll build, and they'll go in their factory, and then people can bring their golf clubs in there to be adjusted. And it has cool vision system, so it actually uses vision to see where that club is and where the lines of the face of the club are, and then it clamps it in and applies a force and clamps and changes the angle of that, and also accounts for spring back. So here's a picture of the clamp where the golf club goes in. And then you can see here's an operator that puts that golf club into the clamp. And here's the output. So you can see there's this bullseye target, we call it bullseye, as to when it's going into, at what angle it is. So you can see this is kind of moving from different degrees depending on how much. So there's a graphical user interface here where the operator can put in how much of an angle they want, and then the machine will automatically bend that club to that, and that you can see on the screen as it's bending how it does it. And so we have a video of this as well, so you can see how that machine works if you wanted to play that video.
Computer, so basically what you do is you'll find the product that you need. So P760s. We'll go in standard adjustment, so I'm not going to need to do anything, but we're still going to check it. So we're going to start with 3 iron, which I have here.
Bullseye's in the name, as you can see.
As you just a little bit into the background. So here, what it's doing is it's taking calculations from the face. So in here we've got a set of cameras, and then we've got 2 cameras, one in here, one in here. And what it's doing is finding the center point of the shaft, and then the best groove on the face to do the calculation. Right. So if we look in here, you can see the face. It's taking the best groove. So it's doing the calculation from that score line to the center point of the shaft, and that will give you the most accurate loft and lie there is.
All right, thank you for that video. And so that when he was talking about the groove, that was that line on the face of the club. And so it's using a vision system to see that line on the face of the club, looking at where that is, and then it applies a very strong force to actually bend the club. All right, and then back to the slides again. We can show you one other example of a project that we've worked on. So this is a CPR training device. And so what this is for, I don't know how many of you have been trained as CPR, maybe those of you who've done a first aid or scouts or something like that, where you have to, if someone is having a cardiac attack or arrest, you press on their chest, you breathe into their mouth, and so you try to resuscitate them. And what the client wanted us to do is to develop a device that would sit on a mannequin, and that would basically be able to tell the user and the trainer how well that person was doing CPR. So this is used in training purposes. So in the past, you'd have an instructor and they'd have all the people in the class and they'd be, doing the compressions and they'd be doing the breaths. And they'd have to watch the person and say, no, you're doing it too slow, you're doing it too fast, or you need to go further or less. And then this is basically a way of doing it automatically. So this loop device that we designed sits on top of the mannequin, and it's got an accelerometer and a gyroscope in it, and it's got a circuit board and a switch so that when it compresses, it then connects to a laptop. And what the client did is they wrote a software game that's kind of like Guitar Hero. So it's like playing Guitar Hero for CPR. So you try to keep the beat, and that's how you learn CPR. So you can see this is the CAD of the device, and this is an expanded, exploded view, so you can see all the pieces that go in it, the circuit board, and then this is a picture of a prototype that we built of this device. And this is a tester that we also built to then test a lot of cycles to make sure it doesn't break. And then here is I think this is our final video of how this device works, if we could play that. So you can see they're putting it on, and then and it has LEDs that change color that also. And then there's the Guitar Hero game in the background. So you can see again, as you press on it, it changes color. It goes green if you're doing it right, and then it tells you if you're doing a good job or if you're missing. All right. And then a few little wrap-ups. So those are some examples of projects that we worked on. If you have any questions on them, again, you can put them in the chat. We'll try to answer those. And then just really quickly, I wanted to talk about what mechatronics is. We've kind of mentioned a mechatronics board, and this whole word mechatronics comes up a bit. And so Simplexity is a mechatronics company, and what that means is it's the intersection between mechanical, electrical, control system, and computer engineering, so computer firmware software. We didn't get into as much on the control systems. We do a lot of algorithms and looking at the whole project as a system and how that works. But we did touch on these other disciplines, and all of that put together is what we consider the field of mechatronics. And so if you're seeing that, it really is looking at the combination of all of those disciplines together, especially when you've got products that you're designing with electronics and firmware and motion and controls and sensors and all of that. This is also a resource, and we'll give you a handout on this in terms of the product development process. And so as you think about how things are designed, we go in different phases. And so we start with phase 0 exploration, and you can see the different curves of when you're kind of doing that exploration versus the engineering work versus this new product introduction, which is more on the figuring how to transfer things to manufacturing, and the building prototypes go throughout this whole process. So we'll give this to you as well, but the main takeaway for you as students is that product development is an iterative process. You don't just build something once and it works. That never, ever happens. And by intent, you're learning the whole time. So as you're doing your own projects and you build something and it doesn't work, don't get frustrated. That is so normal and so natural. And if it ever worked the first time, you should be shocked because that doesn't normally happen. So we, and any product development firm builds in cycles where you learn at each cycle. So you build something, you see what works, you see what doesn't, you iterate, you make it better and better until it's ready to be released. And so depending on the complexity of the project, you'll have different cycles and you'll figure out how long that takes. So for simple projects, it could be a matter of months or half a year. And for more of the complicated project, it's a few years. This is just a slide of an idea. This is our Green Griffiths team. So this is, Kim was the main sponsor, and this is in our San Diego office. So I know Mesa here is in Oregon, but we also sponsored the First Tech Robotics team. And so that is also one of the things that you as a student could do is join other groups. You've got Mesa here, but there are other opportunities to practice your engineering skills. And these are just a few little ending culture slides. So we talked a lot about Simplexity as engineers and what we do, but we do have a bit of fun as well. And so these are just some slides pre-COVID when we could get together, different holiday celebrations. This was about a year ago when we cooked breakfast for the office, had some social gatherings. And this is post-COVID where we have virtual social gatherings where like our summer picnic, instead of all getting together in one location, we deliver food to the office. People can pick it up and cook it in their own backyards. And then we do a Zoom call and try to be social. And we try to have different themes for different holidays. And then one of the other fun cultural thing that we do is we do a Halloween mechatronics contest. And so this is some screenshots of videos from our latest crazy Halloween mechatronics contest. And Kristen was one of the engineers on this team where they built a trick-or-treat candy dispenser. Kristen, is that the best way of describing it? COVID safe, so you wouldn't have to touch to get trick-or-treaters. And they did a video on that. I don't know if you want to say anything about that, Kristen, or not.
It's very fun, and I look forward to it every year. You just get to make something fun with some friends, Halloween themed.
And so these are some pictures from our Halloween themed mechatronics contraptions. And this was from a previous year where Kristen and Eliza had their children, their cute little babies. They made mechatronics wings that flapped as part of their costume, and these were super cute. And this is from a team in San Diego that built this spider that escaped people and with their Halloween candy. And so we have videos on the resources page with all those mechatronics videos of the kind of fun Halloween things that our engineers have built. So I think now we can maybe put the resources up, and then basically on our website under videos, there's a whole section, I think, on culture, and that's where all our Halloween mechatronics videos are, if you want to check those out. And that is the end of the official presentation. So I think we're ready for any questions that you might all have. Hello, are you guys able to hear me?
Okay, Taya, it seems that your audio is still sounding like a robot that's stuck in a closet. So I will I think I'll just facilitate the Q&A portion. For those of you who joined late, you can click on the Q&A, those letters in the top right corner. And if you have a question, you can type it there. All of the other questions that you see, you can click on the thumbs up button. If that's a question that you have as well and you want it answered, make sure to thumbs up and upvote it. We'll start with the question that has the most upvotes right now. So our first question, and I'll let you guys answer, is being a mechanical engineer, do you need to know coding or programming? If so, how in-depth would the understanding of coding need to be?
So for my job as a mechanical engineer, it's certainly not necessary. I work with a lot of mechanical engineers who couldn't write a single line of code if they needed to, but it certainly helps. It allows you to be able to run tests on your own parts and run through scripts, and makes Charles alluded a lot to how much interdisciplinary work there is. And so I don't have to go and bug him every time I need to run a new type of test. I can write or edit a script myself with his help, and so that I can run stuff on my own. So while it isn't a requirement, it certainly helps, and it also just makes conversations with the other teams, or with the other people on your team, a lot easier. If I'm talking to Charles about a firmware requirement I have, if we can kind of speak the same language, it helps a lot. So you certainly don't need to be fluent in every coding language, but having an understanding of how to code and having some experience is certainly a plus.
Yeah, and I'll add to that when we hire people, I mean, it makes you stand out more if you've got more than one discipline, even if it's that you have a degree maybe in one, but if you have projects and you can say that you've also done work in some of the other disciplines, it makes you a stronger candidate. So I encourage everyone to learn as much as you can, especially about things that interest you.
Sorry about that, and thank you for those answers. Anyone else want to do an answer for us? Okay, so I'll move on to our next question. How much math do you need to know to do engineering?
I think it's usually through like advanced calculus. For EE, we definitely had to do a huge amount because a lot of electromagnetism is a nightmare. But yeah, I think just through advanced calculus is what's typical.
Yeah, so I mean, I think I did calculus and differential equations in college, and I have a mechanical engineering degree. So you do have to do some math. You can't not do any. So, but you also don't have to be a math whiz and be perfect at math either to be an engineer. You just have to be willing to learn it and apply it. And I mean, I guess like the other engineers I don't do any math these days other than spreadsheets because I'm doing business stuff. But so I haven't done calculus probably in about 15 years. But I don't know if the other engineers who are working in the field can talk about how much math they're doing now and how much they learned.
Yeah, I was going to say that day-to-day basis, I basically never use calculus anymore, but the fact that I learned it once upon a time is very useful, like understand what the concepts are. Instead, I use a lot of software to do the calculus for me. But electrical engineering basically is just a very simple equation, voltage equals current times resistance, and I use that basically all day long. So not a lot you need to do day-to-day.
Calculus is also a lot easier than algebra. The hard parts of calculus are the algebra, so it gets easier.
Our next question is, what would you say the dynamic of your team is like?
We have a huge range of personalities at Simplexity, and it's awesome. And so you get people with very strong opinions, you get people you have to tease the opinions out of. And the point is that we all get to work in many different teams and learn new skills from each other. You're very rarely on a project completely by yourself. There's usually at least one other person on a project with you. So there are a great many different personalities and personality types at Simplexity.
All right, so I'll move to the next question. What's the most enjoyable part of your job?
I think it's kind of that same thing. It's having a lot of like interesting personalities that you get to work with and learn from every day. Also, I feel like we do a lot of like medical stuff, which is something you can kind of be proud of. Like some of our stuff does like help humans who like need help. So it's kind of cool.
Yeah, and for me, I really like the fact that it's a really great combination of the creative and the technical, because, you know, like we said, we learned a bunch of calculus and we use the concepts that are drawn from that every day. But there's also, when you're designing something, there isn't a step-by-step guide. You have to think in a totally different way to figure out how can these things fit together so that it'll work. When those kind of come together, you can create something that you're really proud of.
Yeah, and I remember when I was doing engineering work, like the first project I designed, I built it in CAD, and like I still remember like I ordered the parts and I got them back on my desk, and I was like so excited. I'm like, oh my gosh, I designed these parts and here they are in real life, and I mean, it was just sort of like, I can't believe that, I get paid to do this, because it was so much fun to like get to create something in like a virtual world and then like get it back. And then of course some of the parts didn't work, I had to fix them, but that was a lot of fun. That's why I liked mechanical engineering, because I like to see things and then build them and then put them together and see how they work. So that was my favorite part of being a mechanical engineer. And then I was a project manager, and I really like organizing things. And now that I'm running the company, it's just different problem solving. So it's like company-wide problems, like how do we make this work more efficiently, and how do we solve this problem so that the engineers can do their jobs, that then we can then create all these cool products for the clients. So it's really rewarding to see the clients with these products that they need, like, the Stera-free Aura is going to help the environment by not having all this wipes being thrown away and waste, and it'll help people from getting sick because their equipment will be disinfected. So it's really rewarding to be able to make some products that make the world a better place in whatever way it is.
All right, so our next question is, what type of design software do you use to design products, both for mechanical engineers and electrical engineers?
So for mechanical, we mostly use two CAD programs. The primary one that we use is called SolidWorks. That's the one that most college engineering programs, I believe, use. And so that is you kind of build one feature on top of another. So you can make a block and then cut things out of it and shape it different ways. And then you can kind of go back through the history. And then there's another kind of design, which is direct modeling. And so Creo is the software that we use for that style. Although that one's a little less popular, that's a little more free form, like you're dealing with a ball of clay, so that you can, when you change something, you don't necessarily go back in time, but you can just play with the existing features.
And for electrical, we use a program called Altium that does both the schematic and the layout steps. I did not learn that in school, though. I don't know if anyone learns it in school. It's kind of crazy. You kind of have to learn on the job. In school, I ended up using KiCad, which is a free version, and Eagle is another free version. And they're all
Eagle.
Yeah.
And in the handouts, I think they're already uploaded. If you have in the handouts, we have the links to that. I think KiCad, right? And then I think Autodesk has some free ones and some other ones, so that you can play around and learn those as a student. I don't think there's free SolidWorks.
No, but Autodesk Inventor is very similar to SolidWorks, and I think it's free if you have an EDU email address.
All right, thanks. And our next question is, how do you plan for different user experience in the design process of your wearable technology, such as people who experience different disabilities, people with different body types, etc.?
I don't know who wants to take that one. We don't do as much of the front end as some, so we usually work with like industrial designers who are looking more on the front end of what the user is going to do. Trying to think if there's an example of, because usually we get the industrial design and we make it all work. And so there's other firms we work with who do that, like talking to the clients about exactly what it has to be. I know I did that a little bit in graduate school, where we were doing that front end part as well. I don't know, Kristen, did you do some of that in other jobs?
Yeah, I agree that pretty often it's our clients who have to do that thinking, but we do get a lot of projects that are like specifically designed for people with disabilities or something. I worked on a pair of glasses that were to help aid people who had vision impairment. So the glasses hooked up to your cell phone, which then would you'd talk to somebody who was your guide. Basically, it was a pretty cool project. So there's some aspects of that where like you have to decide, how does it look? If the person who's using this thing can't actually see it, you need it to be, designed a certain way. So.
Yeah, and my project in graduate school was for permanent crutch users, so people who are in crutches, and they got a lot of repetitive strain injuries in their wrists from using crutches all the time, and so we designed a flexible crutch that had spring motion in it. And so we did actually interview them and kind of had them try the different prototypes and see what they like. And so that it's an iterative process again, where you kind of have people look at it, try it, see what works, they give you feedback. So the best is to build prototypes and get it in their hands, and then they can give you feedback what to change as the users. And then earlier in the Simplexity, or actually previous version of Simplexity history, we built a machine for a voting machine for people who are handicapped. So there was the Help America Vote Act. I think that was a long time ago, but where people wanted to vote. So in Oregon, you vote by mail, so it's less of a big deal. But for states where you have to go to the polling place and vote, the people with disabilities who are either blind or quadriplegic or so forth wanted to vote by themselves without someone helping them. And so we had a lot of input devices in that so that they could vote. There was Braille on it, and there were different ways of inputting your vote. And so there was a whole back and forth as to what was the best way for the people with disabilities to be able to use that machine.
Okay, thank you. Next question is, what does system design mean, and why is it important for a company to work on all stages of a product's development?
So system design was the question?
Yes.
Okay. Do any of you want to take that? Or I feel like I've been talking a lot.
For systems design, we generally consider our systems engineers as ones who help put together kind of all of the disciplines. They put together the circuit boards designed by our electrical engineers, the mechanical components designed by the mechanical engineers. They put together the firmware and software and bring it together as a system, help to bring it up, debug it, and test it. That's what a system engineer is at Simplexity. And the second part of the question was, what was the second part? I'm sorry.
Oh, sorry. The second part was, why is it important for a company to work on all stages of a product's development?
So typically we're hired to do the stages that the client asks us to do. Although one of the newest product or newest services we're providing to our clients is to guide the product not only from the initial design and development and proof of concept, but all the way to the point where it is manufactured and able to be purchased on the market. We don't, as Dorota said in the video, we don't actually do high volume assembly and manufacturing, but we're offering to get the product to that stage to develop a relationship with a manufacturer that will bring your product all the way to your store that you can purchase. So we do enjoy being a part of a project from, let's say, birth through delivery. But generally, we're hired to do whatever stages our clients ask us to help with.
And then I'll add a little bit to what Kim said. The systems engineers also look at, like you don't want to design everything separately. So they're there from the beginning to make sure that all the things work together. So let's say you've got a motor. You don't want just the mechanical engineer to think about, well, what's the size of it? And the electrical engineer say, what's the current draw? You want someone to look at it as a whole system as to, well, what does the motor have to do? And then figure out what is the right type of motor, what is the right size of motor, how often does it have to be run, and then look at the firmware that's going to drive the motor. So it's basically a cross-disciplinary view of looking at all those disciplines together to design an optimized system. So the reason you want somebody who has that systems view in a company like ours that does product development is because then you get better products because you've got someone that's kind of connecting all the pieces together and they're not like all separate. And so that helps kind of bring it all together to optimize it and make it a better product.
And one other note on all working on all the stages of a product's development, because we do often work on a portion where a product has maybe already been started and there's been one prototype, but we need to work on the next section of development to get something that could be brought to market, for example. There's a lot of, we do our best to document every decision we make and why we make it, but inevitably there's going to be some knowledge that's lost. So someone, if they, like Dorota said, if you pick a specific motor, there was probably a ton of thought that went into why do you pick the type of motor, the size of motor, and how it attaches to whatever you're trying to turn. That information might get lost as it transfers from one designer to another. So just having the access to that information all the way along means that you don't have to duplicate efforts. And if you think of a new idea, you know whether that's something that is actually viable or it's something that's been disproven before for other reasons that you're not aware of.
Right, so I think we have about time for one last question. So that question is, how do you communicate among your team when you're all in different places? And I would also add how that changes in the current COVID environment, because we do have multiple offices.
We are on Zoom all day long, and we have not only meetings but constant chats going. Some of you may use similar type systems, Discord, Slack, that type of thing. That's what we do all day long on Zoom, and that's I'd say probably the major way we communicate, although there are a lot of emails that go around all day long as well. So that is, I would say that's been the biggest change since being quarantined or being confined at home since last March.
Another one is that we have a company wiki hosted by Confluence. And so instead of like sending an email like, well, here's the design file and you send it over, instead you can post it somewhere on the wiki and then just send people links. And so then if you want to collaborate on a page together, you can do that and say, add information. You're not just have a bunch of folders on your computer that are difficult to search through. So.
Yeah, and then as part of that, we use SharePoint OneDrive so we can, again, collaborate on files and everyone can edit the file at the same time. So we've tried to get away from attachments to emails because then, you always like, oh, well, which version was that? And that's just not a very efficient way of collaborating. And the thing is, we used Zoom before COVID. So since we have 4 offices on the West Coast, the company meetings, even though I used to do them in the conference room with like the Vancouver office people there was already a Zoom link so the other offices could call in and hear what was going on. So we already like knew how to use Zoom and been using it for years, and we used different platforms before Zoom. And so that in some ways wasn't new. It just meant that we were on it a lot more. So, whereas before it was just when we were communicating maybe with people in the other offices, now it's communicating with people in the same office. And so in some ways it's, while it's harder because you don't see people in person, you can communicate just as well. It doesn't matter if someone on your team is in a different state because, we're in the same time zone. So that makes it just pretty easy. That building hardware is really where we need the offices. As you saw, the time when we're in the office is when we need to use the tools to build the hardware.
All right, so I think that wraps up our Q&A. If you all have more questions about Simplexity, just make sure to visit the website, and also you can click, remember, at the top right on the word handouts, and you'll see the 3 handouts that were provided by the Simplexity team today. I'm going to go over some quick Mesa announcements to wrap up, but I really wanted to thank Kristen, Charles, Kim, DJ, and Dorota for joining us. We really appreciate you all being here today, and especially Dorota, because Dorota has been volunteering with Mesa for most of the year. She's one of our STEM career coaches as well, so I know some of you are joining from part of her coaching pod. Really appreciate you being here today. So to wrap up, I'm going to pull up our slides. We have a couple of announcements. And the first being that this is not the last of our virtual career visits. We're planning to have another one on April 1st with Digimarc. Digimarc is a company located in, I believe it's Beaverton or Tualatin, Oregon. If you're registered for the virtual career visit series, you will get an email reminder the day of the event. If you're not registered, you can register right here. I'm about to drop a pop-up. So if you would like to register for the entire series, you can click on the link there. You can also rewatch today's webinar with Simplexity by logging in at the same link that you see below. Okay. Our next announcement is about our upcoming events for Mesa. So this Saturday, we are hosting our annual Demo Day. Demo Day is time for our Mesa students to present their projects. So these are the design projects that they've been working on this year, a chance for them to receive feedback from different professional reviewers. And we would love any students who aren't planning on presenting, family, friends, to join and see what our students are offering. So that is this Saturday, March 6th, starting at 1 p.m. You can register at the link that popped up below. Also, we would like to offer an opportunity for students to join Invention Bootcamp, which is it's a 7-week-long program hosted at Portland State University, in which students complete a design project. It's led by a mechanical engineering professor here, and it is for high school students. Some of the concepts students learn actually have to do with mechatronics. They'll be using microcontrollers similar to Arduino, which one of our representatives from Simplexity mentioned today. So you'll be learning different aspects of product design. So learning some software, some electrical engineering, and some mechanical engineering to build a physical product. Right now, the camp is going to be running virtually for those 7 weeks. And if you're interested, please sign up today. All right, so I believe that is everything that we had for you today. And I really appreciate having you here. Okay.
All right. Thank you, everyone. Thanks for coming.
Thanks, everyone.